I'm going to start off with an equilibrium state. And an equilibrium state tells me that the energy before must equal the energy after the interaction. I'm in a state of equilibrium in terms of energy here. So now what I'm going to do here is that I'm going to ask a question. What external forces act and do work on a block? So when I look at my picture here, I imagine now that I have my block. So I have a block, and it's going to cross a surface here. And we're going to say here is that here's my block, and I'm going to apply a force in this direction. And what I'm going to do here is that I'm going to imagine that this is the force of a rope or a tension, but I'm just going to call this F. And the other thing that I know here is that I'm going to have displacement in this direction here. Now, there's two ways that we can actually look at this thing. One way that we can look at this thing is we could say, if I look at the network, it has to be the net force times the displacement. If F net is equal to 0, then all forces must balance. And if they balance here, it doesn't matter that there's a displacement. I automatically find that I get 0 times the displacement. So therefore, my net work here is 0, and therefore my change in energy is 0, which tells me that E1 and E2 are the same. That's what I mean by equilibrium, that it looks like this here. But let's look at the details a little bit more clearly to actually get a sense of this. And you know what? I'm not really liking the way I wrote this over here because I'm going to run out of space. So I am going to move this over here. And I apologize if this is causing some issues here because that was not intentional. So if this is the case, then I must have this. So if I draw it this way, what does this really mean here? So I need the details. Okay, so we need the details by drawing a free body diagram. So if I look at my block and I isolate my block, you could imagine that I have my center of mass here, and then I start drawing in my forces. Let's say that I have a force like this. Now, what I know here is that I have a displacement. My displacement is along this direction, and my velocity, I'm going to say, is going to be going to the right with 0 acceleration. So if I write a detailed free body diagram, this immediately tells me that if A is equal to 0, then all forces must balance. So then I start to add all of these things here. So if I break up this force in the Y, and into the X components, I now know how to deal with the force of the rope. But I have a surface force. A surface force implies that I have a normal pointing up, and gravity has to come down and balance those two forces out. And if this thing is moving at constant velocity, then my force of friction, sliding friction, has to balance out f of x. So when I'm looking at these, I see here that there are 5 forces that do work. Well, I should be careful. There are 5 forces that do work where some are 0 and others are not. So what are the forces? We can clearly see that I have f of x, f of y, the normal, mg, and the frictional force. So let's look at these workings, okay? So now, let's analyze these workings. So the first one that I want to look at is that I want to look at the work by f of x. So if you look at this thing, we clearly see that I have a block, and we got to be really careful here. So what do I mean by my block? My block starts here, and my block is constantly moving until it gets to right here. So one of the important things here, if the block is not constantly moving, then no work is done. You have to have a block that is constantly moving. So that means here, I'm going to see here is that there is a displacement from here to here, and I know that I have a velocity with 0 direction right here, and so with 0 acceleration. So then what I'm really looking at is that I'm looking at this force f of x. So for all intensive purposes, that is a classic work, picture of a block going from, point 1 to point 2, and that's how we get that. In the language of the work energy theorem, this is not the physical picture. That's the Newton picture. So what do I really mean by the physical picture? So the physical picture looks something like this. I have a block. And as I have the block, I start to look at this thing and just say, what is my system? And clearly in this case, we can see here is that the system is my block. So then I ask the question, what are the forces acting on, what type of workings occur on this block? Well, we know that the work comes in, and what it does here is that it flows into the system. It increases the overall energy of the system here. So this work of f of x is positive because the force of x and my displacement vector are in the same direction. So, in other words, because my force of x and my displacement are in the same direction, it tells me that the work done by f of x increases the energy of the block. So in other words, it does positive work. So in this case, we then have a situation where we now come in, and if I look at a bar diagram, I could say that here's my bar diagram, and this is going to be my energy state 1. And now I have work that is being done by f of x. And what we know here is that afterwards, the energy of the system has now grown. It goes from energy 1 to energy 2, where the only thing that's meaningful is this part of the graph right there. Why? Because that's the change in energy for the system. E1 and E2 are irrelevant, which is really hard to comprehend. E1 and E2 do not matter. Only delta E matters. So as an example here, to try to tell you that E1 and E2 don't matter, you could imagine that I have an energy state 1, which is 10 joules, and I have an energy state 2, that's 20 joules. So if I look at my picture, I can come over here and I could just say, okay, here's my energy state 1, which is 10 joules. It's right here. And now, what I do here is that I come in and I do work of f of x, and that guy is equal to 10 joules. So what happens here is that in the end, we see here is that the energy 2 has to be 20 joules. And what I'm saying here is that E1 and E2 do not matter. Now, on the other hand, I can do the exact same thing. When I apply the work energy theorem, I could now call E1 equal to 100 joules. And I could say that E2 is equal to, and then I look at the work and I look at the work of f of x, well, that's still 10 joules. So when I look at this thing, you could see here is that I have to scale my energies quite differently now. So now I look at my initial energy, and this guy is 100 joules. But if I look at the work is the same. It does not care what E1 is. All I say here is that I know that I did this amount of work and I get 10 joules. So when I go and I look at this overall system, you could see here is that E2 in this case is then going to be 100 plus 10, so it's 110 joules. So when you're looking at energy, E2 and E1 do not matter. Because in each of these situations, what you're seeing here is that this is E1. Over here, this is E1. So the only relevant piece is this guy right there. The only relevant piece is this one, because that's the only piece that's meaningful. And that's a really hard thing to comprehend. And that's why I'm saying E1 and E2 do not matter. They're meaningless. The only thing that's meaningful is the amount of work that was done. And then that work doesn't disappear. It gets converted into stored work, which we then call energy. So let's keep moving. So we just talked about the work done by f of x. Now let's talk about the other work. So when you look at this other one here, we're going to talk about the work of friction. And so if we do the same thing as we did over here, we're looking at this guy. And so what's happening, if I take Newton's laws pictures here, maybe how about if I just copy this here, since it's already right here. Let me copy this. So if I paste this guy right here, the only thing that matters is that if I look at a picture, I'm now seeing that I have a frictional force going in the opposite direction while the displacement is going to the right here. So if I have the exact same language as before, what am I seeing here? What I'm seeing here is that I focus on the work energy language and we start to draw a system. So in this case, we then say, from the work energy language, I have a block, and this is my block. So when I look at this block, what I'm seeing here is that there's a couple of things that are going on. One, I see that the force of the friction is in the opposite direction of the displacement, since this guy is moving to the right. So when I look at my system here, I should have moved, I'm going to move this over here. So when I look at this thing, I am clearly seeing that I am pulling something out of the system, because now I could say here is that the work of friction is negative. Because of those two things like this following the same language as we did up here, because these two guys are in opposite directions, that work then decreases the energy of the block. In other words, because this guy and this guy are in opposite directions, there is negative work that reduces the energy of the system. And so picture-wise, we start to look at it in a bar diagram, just like we talked about before. So if I look at my bar diagram, what I'm seeing here is that if I'm reducing the energy, that means I must be doing what? I must be reducing the available energy. So if I look at this energy here, and you can see here is that this is a high energy state compared to before. And now what I do here is that I do negative work here. So this external work decreases, it pulls energy out of the system. And as a consequence, this energy decreases to energy 2 here. So again, what is meaningful? What is meaningful is this quantity right here. There is a negative change in the energy of the system. Once again, this is meaningful. Whereas energy 1 and energy 2 are meaningless. So now I could then go in and I could talk about the zero workings. So if I look at the zero work, then when I look at my block, I see that I have 3 forces that have zero work. Why? Because they're perpendicular to the system, or to the direction of the motion here. We have the normal and we have mg. These guys are perpendicular to the displacement. And because they're perpendicular to the displacement, we then say that if I have a force that's perpendicular to the displacement, that implies then that the work of the normal, the work of Fy, the work of mg, they're equal to 0. I mean, let me be careful. These works do not change the energy of the system. And even though I said it and I started to write it, but I didn't finish, these are all 0. So the energy stays the same. So now I could come in and apply the work energy theorem here. So now the work energy theorem tells us that I have a block. The only thing that matters in this block here is that I can, if I have a displacement in this direction as this thing moves at constant speed, then what I'm really seeing here is that when I look at my system, what am I seeing? The only thing that's relevant, according to a free body diagram, is that I have a force that's pointed in the same direction of the displacement. I have a force that's pointed in the opposite direction of the displacement. So then when I start to look at this thing, I have flow, energy flow for the system. In other words, I have the force of X adding energy to the system. I have the work done by friction. It's taking energy out of the system. And as a consequence, we then say that the network, which will then be the positive of the work of f of x minus the work of f of k. And because these guys balance each other out to be in a state of equilibrium, then this tells me that there is no change in energy. So what we're seeing here is that these two workings balance each other out. They balance each other out. So when I look at my bar diagram, what does my bar diagram do here? Remember, E1 and E2 have no meaning whatsoever. I have my energy. So looking at this thing, what happens to the work of f of x? Well, it increases the available energy to the system. That's what it does. But at the same time, the work of friction decreases the available energy. So when I start to add these, you're seeing here is that these workings offset each other. In other words, they balance so that my energy afterwards, E2 is the same as E1. This tells me here is that energy-wise, the system is in an equilibrium state. Since E1 is equal to E2.